Today we are going to be talking about acid and base balance. The foundation of acid-base balance in the body is this equation. CO2 plus H2O equals H2CO3, which will equal HCO3 minus plus H plus. Note that each part of this equation has an equal number of carbons, hydrogens, and oxygens. They are just combined in different ways throughout the equation. Now, carbon dioxide is relatively stable, as well as water. They don't normally blend well or like to combine under usual circumstances. Think about that last can of soda you left out that lost its CO2 and went flat like water. So in order to combine these two molecules together, an enzyme is required. That enzyme is carbonic anhydrase, abbreviated Ca. Once carbonic anhydrase combines CO2 and water, it will make H2CO3, or carbonic acid, which is relatively unstable and wants to break apart. When it breaks apart, it will usually separate into bicarb, HCO3 minus, and a hydrogen ion. Hydrogen ions are usually acidic. Bicarb is a base, being the opposite of the hydrogen ion. It can accept the positive hydrogen ion, which is an acid, removing it from circulation and neutralizing it in the body. Bicarb and hydrogen are naturally attracted to each other because of their opposite charges. When they combine together, they create carbonic acid again, the one in the middle. Carbonic acid is unstable and will break apart into CO2 and water again. This process of the things on one end of the equation combining together to make the compound in the middle that breaks apart, creating the substances on the other side of the equation, is called an equilibrium reaction. This process will go back and forth across the equation depending on which ingredients are currently present. Before we continue with this equation, we need to make a simple connection. If we simplify this equation, we reach CO2 equals H plus. Remember, H plus is an acid. So if CO2 equals H plus, then the more CO2 means more H plus, or more acid. So in that sense, CO2 is acid. Suppose in this equation, I add more carbon dioxide. CO2 is now very likely to combine with water, creating carbonic acid, moving across the equation to create on the other side bicarb and hydrogen. This is an example of a right shift. You can think of this as pouring CO2 on one side of the equation and watching the reaction run over to the right side. Now if we want a left shift to occur, we will add either hydrogen or bicarb, pouring either of those two on the right side of the equation and watching the equation flow to the left. Now what would happen if instead of adding CO2 we removed it by sucking it away like a vacuum? Removing things from one end of the equation creates a hole, causing the substances on the opposite side to try and fill it. For example, removing CO2 will create a hole, causing bicarb to combine with hydrogen, creating a left shift to try and fill it. How does all this relate to acid-base balance? Well, remember, bicarb is basic and hydrogen is acidic, and CO2 is equal to hydrogen. Simply put, we have one thing that's basic and two things that are acidic. If I add acidic things, then I become more acidic. And if I add basic things, then I become more basic. And if I remove one of the two, then the other becomes more dominant. So if we remove CO2, an acid, then I must become more basic. The last piece of acid-base balance is that the left side of the equation is controlled by the lungs, or the respiratory system. The right side of the equation is controlled by the kidneys, or metabolic side. For example, if an individual breathes quickly or hyperventilates, they breathe off more CO2, an acid, leaving a hole on the left side which will cause the metabolic side to rush over and try to fill it, creating a left shift. Because during hyperventilation the CO2 is lost, which is an acid we just talked about, will make an individual more basic. In this scenario, when an individual hyperventilates, it makes them more basic and is caused by the respiratory side. This is called respiratory alkalosis. Now what would happen if the kidneys began to reabsorb bicarb, adding it back into the bloodstream? So we will have an added bicarb to the right side, the metabolic side, causing a flow to the left, or a left shift. Remember, it was a base that was added, bicarb, so the individual is going to become more basic. This is called metabolic alkalosis. Note that in the first scenario, we removed CO2, an acid, making you basic, and in the second scenario, we added bicarb, a base, making us more basic. Now let's apply this to some acid-base balance questions that you see on a test or in a hospital setting. In order to discover whether something is being added or taken away to the equation, we have to know some baseline numbers. The normal pH in the human body is about 7.35 to about 7.45. The normal CO2 amount is about 40, and the normal bicarb amount is 24. Suppose you receive a patient in the hospital, and then you get their blood work back as well. And the blood work says that their pH is 7.48, CO2 is 35, and bicarb is 21. The first thing to do is to determine if the patient's pH is acidic or basic. Everything above 7.45 is basic, and everything below 7.35 is acidic. When we compare the 7.48 pH to what is normal, we can see that the individual's pH is higher or more basic. The question now is, one of these other numbers is either causing the problem or which one is trying to fix it. CO2. CO2 is low, and would low levels of CO2 make someone more acidic or basic? Remember, CO2 equals H+, an acid, so we treat it like an acid. So if CO2 is low, or the acid is low, then that means the low levels of CO2 are basic because we have less acid. Does the low levels of CO2 match the patient's current pH? Yes. The patient is basic, and the CO2 levels are agreeing or match the patient's pH, making it basic. Now let's look at bicarb. The bicarb levels are also low. Would low levels of bicarb, a base, make a patient basic or acidic? A low base would mean you would have to become more acidic. So the low bicarb is doing the opposite. It is trying to fix the patient's pH of 7.48, their basic blood. In other words, CO2 is causing the problem, making the individual more basic, and bicarb is trying to fix it, making them more acidic. In other words, CO2 is causing the problem, making the individual more basic, and bicarb is trying to fix it by making them acidic. Remember, CO2 is on the respiratory side of the equation, and bicarb is on the metabolic side of the equation, trying to compensate for the alkalytic problem. So respiratory alkalosis with metabolic acidosis trying to compensate. Let's look at another patient or test question. This patient has a pH of 7.33, a CO2 level of 47, and a bicarb level of 27. Do the same steps as before. Start from the top and determine if they're acidic or basic. While comparing the pH to normal, 7.33 is acidic. Now if we look at CO2, would high levels of CO2 make someone basic or acidic? High levels of CO2 are going to make someone acidic. The pH of the patient is acidic, and the CO2 levels are acidic as well. These two match. Now bicarb. Bicarb levels are high. Now does someone with high levels of bicarb make them acidic or basic? High levels of bicarb are going to make them basic, so this is the opposite of the problem. This means bicarb is trying to fix the problem. So we would diagnose this patient with respiratory acidosis with metabolic alkalosis trying to compensate to fix the problem. Thank you so much for watching this tutoring video on acid and base balance.